Have you ever really stopped to think about how a program decides what to do next? It's not magic. Not at all. It's all about logic. It's about us, the programmers, giving the computer a roadmap of rules to follow. So today, we're diving deep into the very heart of C programming, control flow. We're going to learn how to teach a computer to make decisions and repeat tasks, turning these static lines of code into a dynamic, well, almost a thinking process.
So let's just start with a big fundamental question. How in the world do you teach a chunk of metal and silicon to think, to actually react to what you're doing, to choose between path A and path B, or to do something 1,000 times without you having to tell it every single time?
Well, the answer is surprisingly simple, but also incredibly powerful. You just give it rules. That's it. You don't just program a computer. You're more like a teacher, showing it how to follow instructions based on different conditions. As the programmer, you get to be the architect of its logic. You literally control its flow.
All right, let's jump right into our first section. From yes-no to many paths. We're going to start with the most basic building block of decision-making, and then see how we can scale that up to handle a whole spectrum of possibilities.
Okay, so this is where it all begins. The good old if-else statement. I want you to think of it like a fork in the road. The if part asks a simple question. Something like, is the user older than 18? If the answer is yes, boom, we go down one path. If it's no, the else kicks in and we're sent down the other path. It's the simplest, most fundamental decision any program can make.
That's great for a simple yes or no, but, well, life is rarely that simple, right? Think about something like a grading system. It's not just pass or fail. You've got A, B, C, D. You need a structure that can handle a whole sequence of choices, not just one.
And for that, we have the else-if ladder. It's exactly what it sounds like. The computer checks conditions one by one, right from the top. If a condition is false, no problem. It just moves down to the next rung. But here's the key. The moment it finds one that's true, it runs that specific block of code, and then, this is important, it skips the rest of the ladder completely. This makes it super efficient. And it's exactly why the order is absolutely crucial. If you check for a score above 33 before you check for a score above 90, your A+ student is just going to get a pass instead of an A. Not good.
So the else-if ladder is awesome, but when you've got a lot of very specific fixed options, like a menu with choices 1, 2, 3, or 4, checking each one in order can be a little slow. Sometimes we need a more direct route.
And this analogy just nails the difference. Think of else-if as taking the stairs. To get to the 5th floor, you have to pass floors 1, 2, 3, and 4. The switch statement, that's the elevator. You press the button for floor 5 and it takes you directly there. It doesn't care about the other floors. And the reason it can do this is because under the hood, it often uses something called a jump table, which makes it incredibly fast for matching one value against a big list of constants. But, that elevator-like speed comes with some very strict rules. Switch just can't handle flexible conditions like greater than. Nope. It needs exact integer or character values for its cases. And that last point about break is a classic trip-up. If you forget to add a break, the code doesn't stop. It actually falls through and starts executing the code in the next case too. It's a feature that can be really powerful, but also really dangerous if you're not paying attention. Okay, so far, we've only made decisions that run one time. But the real power of a computer, its superpower, is its ability to do boring, repetitive tasks over and over without ever getting tired. And for that, we absolutely need to master loops.
Let's start with two fundamental types of loops, and I love this analogy. The while loop is like a bouncer at a club. It checks your ID, that's the condition, before you get in. If the condition is false from the get-go, you're not getting in the club. The loop body never, ever runs. The do-while loop, on the other hand, is like an all-you-can-eat buffet. You always get to grab a plate and serve yourself, run the code, at least once. It's only after you finish that first plate that it asks if you want to go back for more. This guarantees at least one trip through the loop.
Now, while those other loops are really useful, the one you're going to see most often is the for loop. And it's a favorite for a really good reason. It's just so clean and organized. It puts the three essential parts of any loop, the initialization, the condition, and the update all together in one single tidy line. This makes the code so much easier to read and, believe me, to debug. So we've covered the main roads of control flow. Now let's talk about the shortcuts, the back alleys, the expert techniques that give you even finer control over your program's logic.
All right, now for a concept that trips up so many programmers, especially in interviews, short-circuiting. Take a look at this condition. We're checking if A is greater than 100 and if B++ is greater than 0. So let's imagine A is 10 and B starts out at 5. Go on, take a guess. What will the final value of B be after this line of code runs?
Let's walk through the computer's logic here. Step 1, it checks the left side. Is A, which is 10, greater than 100? Nope, that's false. Now, because we're using the AND operator, the computer is smart. It knows that if one part of an AND statement is false, the whole thing has to be false. There's literally no reason to even look at the other side. So, it just stops. It short circuits. And that B++ part, it's never ever touched.
And there it is, the final answer. Because the right side of that condition was never even executed, B was never incremented. Its final value is still 5. And remember, this isn't a bug. It's a vital efficiency feature built right into the C language.
Inside our loops, we have two more really cool tools for fine-tuning. Break is basically the emergency eject button. The second the code hits break, you are thrown out of that loop entirely. No questions asked. Continue is different. It doesn't end the whole loop, it just ends the current cycle. It basically tells the computer, hey, I'm done with this one, let's just skip to the next one, right away.
And then there's goto. This might be one of the most controversial statements in all of programming. As the legendary computer scientist Edgar Dijkstra famously warned us, it's a tool that can turn your clean, structured code into an unreadable, untraceable nightmare known as spaghetti code.
For decades, using goto has been seriously frowned upon. But it does have one very narrow use case that's sometimes considered acceptable, escaping from really deeply nested loops. See, a single break will only get you out of the innermost loop. A goto, however, can act like a teleporter, jumping you out of all of them at once to a specific error-handling spot. But I have to say this again, this is a tool of last resort. Use it with extreme caution.
Phew! Okay, we have covered a lot of ground, from simple decisions to complex loops and these crazy jumps. So, how do you know which tool to pull out of the toolbox and when? Let's put it all together.
And here it is, your C-Control Flow Toolkit. This chart really summarizes everything we've talked about. You use the if-else-if stairs for those ordered checks, you take the switch elevator for fixed options, use the while bouncer if you might loop 0 times, or the do-while buffet if you know you need to run at least once. And for most loops where you're just counting, the all-in-one for loop is almost always your best bet.
So there you have it. We've seen exactly how to give a computer a set of rules, from these simple branches to complex repeating logic. You now have the fundamental tools you need to control the flow of any program you can imagine. The only question left is, what are you going to build with them? What set of rules will you write first?